Now we've seen what the inverse matrix is, and we've also seen that linear systems can be written in the form AX equals B. Now I'd like to use the inverse matrix to solve linear systems. So let me remind you of the pertinent information. So recall that the inverse matrix satisfies that A times A inverse is the identity matrix. The identity matrix is the matrix that has ones along the main diagonal and zeros elsewhere. This is like the number 1 because if you multiply any matrix times the identity, you just get back what you started with, the matrix A. And usually you cannot reverse the order of matrix multiplication, but if you're dealing with an inverse matrix, you can, and you still get the identity if you multiply them in the opposite order. In this class, we're not going to give the method to find an inverse matrix for larger than 2 by 2. If we have a 2 by 2 matrix with entries A, B, C, D, then the inverse matrix is given by 1 over AD minus BC times the matrix that you find by switching the diagonal elements, so DA, and then negating the off-diagonal elements, so negative B, negative C. Now, of course, this only works if you're not dividing by 0. So this works when AD minus BC is not equal to 0. If this is equal to 0, then the matrix does not have an inverse. Not every matrix has an inverse. Okay, so let's do an example here. Let's solve the linear system 2x plus y is equal to 3 and 4x minus y is equal to 1. Now we could solve this using substitution, we could solve this using the elimination method, but I'm going to solve this problem using the inverse matrix just to illustrate how that goes. So this is the same as writing the matrix multiplication 2, 1, 4, negative 1 times the column vector xy, and that should equal 3, 1. That's writing my system in this form. A matrix A times a vector x of unknowns equals a vector b of constants. I will now multiply both sides by the inverse matrix. So if I multiply both sides by the inverse matrix, I get 2, 1, 4, negative 1 inverse times 2, 1, 4, negative 1 times the column vector xy should equal 2, 1, 4, negative 1 inverse times 3, 1. So what I did was multiply both sides of the equation by this inverse function. Now what happens is this side is just the 2 by 2 identity, 1, 0, 0, 1. And if you multiply the identity times anything, you get back itself. So this side of the equation just becomes simply xy. This matrix and its inverse cancel each other out, just like a function and its inverse undo each other, such as e and log. This side, however, I can use our formula for a 2 by 2 inverse. So I get 1 over AD minus BC. So AD would be negative 2 minus BC. So BC would be 4. So I get negative 1, 6. The formula would be to swap these two entries. So negative 1, 2, and put negative signs here. Negative 1, negative 4. And I'm going to multiply that times the vector 3, 1. So then you could do this matrix multiplication, and I'd get, I believe if you do the calculation, 2/3 and 5/3. So this is my answer. Now admittedly, if you have a 2 by 2 linear system, finding the solution with the inverse is more work by hand than by doing the elimination method. However, when you continue on and use matrix algebra and solve large linear systems, it's convenient to have as many methods to solve as possible, including the inverse. If you go on in the theory, this is a key concept to understand. Let's do one final example. What if we do a super general example? What if we do the most general 2x2 example possible? What if I need to solve ax plus by is r, and cx plus dy is equal to s. So here I'm assuming that a, b, c, d, r, and s are constants that I know, and the variables I'm trying to find are x and y. Well, this is the matrix multiplication a, b, c, d times the vector xy is equal to the vector rs. If I want to undo matrix multiplication on both sides, I can multiply by the inverse. So if I multiply by the inverse on the left, the inverse and this function undo each other, canceling one another out. And on the left side, I'll just get xy. On the right side, I'll get the inverse, a, b, c, d inverse times rs. If, maybe I should say, AD minus BC is not 0 here. If that's the case, then AD minus BC times DA, negative B, negative C, RS is my answer. And I get 1 over AD minus BC, and I believe if you do this calculation, you will get dr minus B times S divided by negative CR plus A times S. So there's a general formula, provided, of course, that this term is not 0. If this term is 0, then that means we're going to be in one of the situations where we either get no solution, where we have parallel lines that don't intersect, or we get a single solution, or we actually get an infinite number of solutions when those two lines are on top of one another. Okay, well, here is an introduction on how to use the inverse matrix to solve linear systems. Excellent.